I welcome you all on behalf of ICC for the session 3C session for
Thank you very much. Today's topic is research and development of hydrogen technology and hydrogen storage. Next slide, please. I want to start from the characteristics of hydrogen technology, especially for global environmental protection. First one is hydrogen can be produced without CO2 emission, electricity utilizing renewable energies, and fossil fuel with CCUS. Second is hydrogen can be transported for a long distance and stored for a long time. A long distance, long time storage by pipeline, liquid hydrogen, and also ammonia and MCH is very good candidates. Hydrogen can be utilized without CO2 emission, hydrogen power generation, fuel cell, and energy conservation in industrial application areas. Therefore, hydrogen is one of the most important technologies for zero emission of CO2. Next one, please. This is an overview of hydrogen technology. Energy sources and production is the first one, and transport and storage and utilization. For production, fossil fuels and also renewable energies. And CCS is very important factors. And for transport and storage, this is main topics of today. Compressed hydrogen and pipeline is a very short time range. And liquid hydrogen and organic chemical hydride, ammonia, and is a very long range. And metal hydride is another applications. I want to explain about the hydrogen strategy around the world. Basic hydrogen strategy has been firstly established by Japan in 2017. That is very recent. And France, Korea, EU, Germany, IEA publishes a strategy, and also India powering India hydrogen ecosystem is today's one, and the national hydrogen mission will be soon in this year, I hope so. Next one, please. I will start with hydrogen production without CO2 emission. And the hydrogen cost varies greatly depending on technology and regional characteristics. Cost of renewable energy is very important functions. Under low-cost renewable energies, hydrogen production costs of $0.15 US for normal cubic hydrogen. So in India, you will realize this kind of cheap one. And in Europe, more expensive. For Japan, a little more expensive. That is the truth. Next one, please. Transport and storage of hydrogen. There are several carriers candidates, and extremely important for establishing the international supply chain of hydrogen. That is, long distance transportation is essential. And Japan has much stress to develop these technologies. Carrier candidates, liquefied hydrogen, that is 1/800th volume of compressed hydrogen, high purity hydrogen, that is very good characteristics. Organic chemical hydride is another candidate. A liquid chemical product at room temperature and pressure, such as MCH, methylcyclohexane, is one candidate. And ammonia is also another candidate. Higher volume hydrogen density is good, but not converted again to hydrogen because much amount of heat is necessary for that. Pipeline is mainly domestic transportation is very important. And metal hydride is very safe and safety is very high. And it's good for buildings and for forklift mobilities. That is good in factories. These are candidates. Okay, next one, please. That is a project of international hydrogen supply chain that is converted to hydrogen carrier. For example, overseas hydrogen resources, brown coal, byproduct, associated gas, or green gas, converted to hydrogen carriers such as liquid hydrogen, organic chemical hydride. In Japanese cases, liquid hydrogen is from Australia to Japan, organic chemical hydride to Brunei to Japan. That is the trial is under development. And hydrogen utilization in Japan, large scale electric power generation, and also energy storage by hydrogen. Hydrogen is very easy to storage the large amount of energy. Next one, please. It's a utilization technology of hydrogen. That means on the upper figures, demand of hydrogen is expected to grow by 2050, very rapid growth. And Japan has a good hydrogen power generation technology that has been utilized through overseas project that is for power generations. And also on the bottom figure, hydrogen power generation, fuel cell vehicles, petrochemical steel making, and also stationary fuel cells is very important. These are the very important utilization technologies of hydrogens. Now, I will explain about the energy storage more. Next one, please. This is a figure between power and storage durations. And you can see the horizontal line is storage duration that is started from millisecond to minutes, hour, day, week, months, and seasons. And the vertical line is power. And you can see pumped hydro and hydrogen is not appeared, but this blue line is hydrogen, and battery is on another one. And nowadays, about 99% of energy storage is by pumped hydro. But in the future, hydrogen and battery is very important. Especially blue one is hydrogen, and hydrogen has a characteristic to higher power and longer duration. That is, for months or seasons, it can storage. That is very important characteristics. I will explain a little about the liquefied hydrogen next. Next one, please. This is liquefied hydrogen. Density is very large compared to the hydrogen gas. And for liquefied hydrogen, latent heat and sensible heat of minus over 200 degrees is necessary. But the compared to the caloric value, combustion value is only 4%. Therefore, not large amount, but to make such a very extreme low temperature is to realize that one is much amount of electricity is necessary nowadays. That is a difficult problem still. Next one, please. And let's image the hydrogen production amount by photovoltaics. That is green hydrogen. And hydrogen, please imagine the 1 megawatt mega solar. That is electricity generation is annually 1,000 megawatt hour. That means by use of electricity, hydrogen production rate is for annually 18 ton. That is for every month. That means 70,000 cubic meters. And liquefied hydrogen, 21 cubic meters, that one. And if you imagine the 1,000 of mega solar, that is 1 giga solar. That means you can see 17 million cubic meters for months. That is imagine with 100 atmosphere, over 55 meters cubic one is necessary. That is very huge one. And for liquefied hydrogen, 21,000, that is about 28 meters cubic one is necessary. That is more reasonable. And that is the image of hydrogen storage for 1 month. That is a very important characteristics of hydrogen. Next, please. Now, about discussing about the hydrogen, it's necessary to estimate how much amount of CO2 can be reduced by utilizing hydrogen. This is a very important estimation. And in this case, by power generation, we can see about 190 or 580 million ton can be decreased globally. It can be estimated. And next one, please. Also important one is the cost of CO2 reduction. That is, say, CO2 abatement cost. And in this case, still very expensive for CO2 reduction because hydrogen is very expensive now. But in 10 years, it becomes 1/3, and in 20 years, it becomes 1/5. In that case, it is same as the LNG power plant. That means it's very important that this kind of decrease is established by technology development. This technology development is very important for making the total cost of CO2 reduction can be reduced. Next one, please. Therefore, we should make the technology development to decrease the total amount of cost. That is about $10 trillion annually. That is very huge one. Therefore, we should make the much effort to research and development of various kind of technology, especially hydrogen is very important one to make the total cost to be decreased. Okay, next one, please. And one message from, next slide, please. And one message is for that purpose, global collaboration is very important. Estimation of CO2 reduction and also technology development is very important for collaboration. That is one message from me. And the summary is the next one. Next slide, please. And hydrogen technology is very important for decarbonization of many fields. And Japan has very struggling with as one of the pioneer. And production cost depends on the production technology, especially the climate characteristics of, for example, solar one is very important. and long distance transportation, and that including hydrogen storage is very important for international supply chain. And Japan has also making efforts for that, and reduce the cost of hydrogen should be globally collaborated to realize. Thank you very much. It is my brief introduction of as a keynote speech. Thank you.
Yeah, thank you, Dr. Akira. It's a good presentation. Can I ask you now?
Yes, please.
Yeah. See, you are using all colors of hydrogen,
Yes.
not only green. So how do you address the climate challenge?
Pardon?
How will you address the climate challenge? Example, CO2 emission, because you are planning to use all sorts of hydrogen.
Yes, yes.
All colors, yeah.
Yes, that means two methods is very important for the renewable energy as much as possible.
Yeah.
That is one, and also fossil fuels, blue hydrogen with CCS is very important. These two should be parallelly developed. That is very important.
Okay.
Okay.
And do you have any storage cost comparison between your liquefied hydrogen and MCH and metal hydrates? Electrolysis is expensive, but does it come under $1 per kg?
Yes, I explained there are three candidates, and that is not only storage, but also long distance transportation. That is combined technologies.
Yeah, okay, yeah.
And that is, this one method is suitable for one case. Another one is, that depends on the situation. Therefore, these three candidates has some good solutions at each other, I'm thinking.
But at the moment, they are all at the cost limit of $1, including storage and transportation?
Yes, in Japan, we are parallelly challenged. And with the international collaboration is very important. Therefore, with some countries, we are trying internationally.
Right. Your brown coal project is coming under $1?
Yes, brown coal
from Australia.
Yes.
Coming under $1 or still higher?
Yes, and also natural gas plant with Brunei is making MCH, and ammonia with Saudi Arabia, like that.
Okay. Any of you want to ask some few questions? Okay, maybe we'll have it at the end of the other panelists. Now I invite, we have two speakers. May our two panelists, one Professor Jayant Singh from IIT Kanpur. He works in the area of material and biomolecular modeling, thermodynamics of complex fluids, machine learning, discovery of new materials, and specialty chemicals and drugs. His group develops tools, algorithms, and also work on product development in the lab scale. And articles with the international.
Rather than giving a complete presentation. Hope you can see that. Thank you for the kind introduction. So already the foundation of this session has been laid by Dr. Yave. So I will just specifically address key questions related to materials, related to storage. Why hydrogen, we all know now. So I won't go in too much in detail. One of the key factors which is driving this is the CO2 emissions, and we want to decarbonize the sectors. And therefore, all across the countries have a certain missions to accomplish, and which is enhancement in the global market, and that's very clear. Existing growing demands are pretty much very well known. Mainly it's ammonia which is being used, and that's why this is related to CO2 emission as well. But there are significant emerging future demands, which includes the transportation and certainly the other kind of applications. Just a second. So sorry about that. Basically, all across this, one of the important factor while you talk about the production, transportation, is in the future needs which we are aiming for, is to have a right kind of storage. And that is something of the biggest challenge in last so many years. So onboard storage is one of the classic issue which is not yet, I mean, people have tried, but it is not yet able to meet the requirement as far as to make it commercially viable. So if you look at the volumetric capacity of the hydrogen storage versus gravimetric capacity, this is the range wherein the many automobile industries have looked at, and these are all compressed hydrogen. But the real need is something which is far above. And this is where the kind of storage we are talking about, which is its requirement. While we are currently looking in both aspects of that, one is a physical based, where this has been already talked about. The one material base which has shown these significant possibilities. And this is why you see a large number of different kind of materials have been synthesized, tested, and being currently researched at different groups. And this is where it becomes an important, so I won't talk about much of a physical based storage. I mean, of course, this is well researched, and there are still additional R&D efforts are needed in order to ensure the cost and the safety of it. That is one aspect people are looking at, which is something which is immediate need. But then there's a material-based storage, which is a long-term solution for particularly the onboard and many other some kind of portable applications. You can categorize it in 3 different kind of materials, which are commonly currently the kind of hot materials. One is material hydride. And the challenge here is to improve the volumetric and gravimetric capacities, and particularly the kinetics of the adsorption and desorption, which is a primary concern. And of course, the other things are cycles and the reaction thermodynamics. Understanding that also creates new possibilities and controlling the whole reactions. Then there is a chemical hydrogen storage. Again, the similar kind of challenges we have is to improve the volumetric and gravimetric capacity, improving the transient performance, and particularly when it is a chemical, there is a release of the volatile impurities, and that is something which is also a cause of concern. Now, the third category is a sorbent material, which is nothing but adsorbent, and this is where the temperature plays a significant role, because it is not a chemical-based adsorbent, it is a physical-based, and there where this kind of strong binding is necessary, and that is where the temperature plays a role. Again, the same issues are there. So in this case, mostly people are looking at different possible pore sizes and surface area to do that. So if you look at all possible combinations of across, let's say 400 of these materials, and put down this in terms of the hydrogen capacity and this temperature base, the system target is somewhere here. Most of the metal hydrides lies much higher in temperature, and though they have a higher capacity, but it also have a very higher temperature, and this is not amenable to the practical conditions, what we want to lead in reality. And then you have this chemical hydrogen, which is somewhere here. Some are very close, particularly this, if you look at aluminum hydride and so forth, these are very close to the realistic conditions. However, still is far from the real, the actual conditions, what is the system target. And then you have this adsorbent, which are, of course, at low temperature, though it is a very high capacity, but again, the same issues are there. So these are the storage target. I've taken it from the recent white paper. But you may ask the question, what is the kind of a cost? And you can clearly see the metal hydride per system is quite low vis-a-vis the sorbent and chemical hydrogen. So a lot of interest in these things are there. However, I can clearly see there's still a significant challenge in this as of now. So if you put it in terms of the issues of the challenges, the weight, volume, efficiency, durability, refueling time, cost, and particularly codes and standards. So once you have it, you really have to understand the code and standards so that it is either interfacing with different units, particularly in, let's say, in onboard and other. They need to be standard to make it viable in industrial scale. And the life cycle and efficiency. These are the broader challenges which one should look at it. And perhaps a more relevant later part from the industry point of view. So there's a lot of thrust, as we clearly understand, because of the different streams of the possibilities, and hence, and some are short-term, some are long-term. But what my group is trying to do is to look at possibility of coming with an automated way, speed up the discovery and optimization of the hydrogen storage. And this is where essentially we have built up or building up tools which can accelerate. This is with this prescience in silico, which we work on. Here, the idea is to basically use atomistic informations of these materials, use high performance computing. And before going to the experimental bed, one should have these possible combinations which can be the realistic kind of materials. And this is where the technology of this nature, where you bring the physics base, that means your quantum chemistry as a part of it, the reaction mechanism, everything is developed in silico, and using these very high-tech techniques to minimize the time to discover materials. And that is what I believe that in future we really have to use these things for accelerating the discovery of the material as per the requirement of the technology. So with that, I will stop. Thank you very much.
Yeah, it is indeed a good presentation, and it is okay. There are a empty number of materials available in the literature, but accelerating that and high throughput is one which is missing. So I think it's a very good attempt, and we need that in India at the moment. So hopefully many researchers will be interested in that to take care of all this throughput increasing the materials. So in fact, DST also has launched a special program called the Material Acceleration Program. I don't know whether you...
I'm part of that. I'm part of that.
That's very good, actually. Yeah. So now maybe we'll go to the third speaker, and then we'll have a good discussion. So I'll just introduce the speaker now. We have a third speaker, Mr. Ravindra Vasisht, Regional Director from Hexagon Agility, India. And he's basically an electrical engineer and a postgraduate from the Institute of Rural Management. For about 36 years of corporate experience in the field of sales, business development, and corporate strategy. And he has a wide industrial experience in food, plastics, automotive, healthcare, defense. For about 11 years experience in natural gas, clean energy with the Hexagon Agility. He has worked in reputed organizations like NDDB, Alpha Level, Nipro, Tata Group in the past. In Hexagon Agility, he introduced the concept of composite type of CNG and hydrogen cylinders to India. The first CNG bus with a range of about 1,000 kilometers in India. He is a voracious reader, writer, and keen interest in defense, the strategy in politics, good sense of humor, and enjoy traveling. Let's welcome him for this ICS Summit 2021 to present his Type 4 cylinders. Welcome you, sir. You are muted. You are muted.
Thank you so much. Really feel proud to be here. So let me just start off without much ado. I hope you're able to see the screen. See, the Hexagon group has a very simple three-word vision and mission that we have, which is about clean air everywhere. Without going into a lot of explanations about what we would like to achieve and do. We are a very high growth technology company, and Mitsui Japan is our largest shareholder. We've been manufacturers of composite cylinders for the last now almost 50 plus years, of which in the commercial space we have been since about 2005. This is headquartered in Ålesund in Norway, about 800 plus employees, and it's publicly listed on the Oslo Stock Exchange. If you look at our global business areas, we are into LPG cylinders, again with composites, then the mobile pipeline, which is for transportation of gas, light duty vehicles, heavy duty vehicles, and then hydrogen products, which have been used on applications like trains and ferries in Europe. And we have about 25 locations worldwide, including 10 manufacturing and assembly locations that we have. If you look at our product competencies, it varies from energy storage to energy management, the system integration, the user interface, all of that. And we also have a complete system capability for the entire system solutions that a customer would require on any of these solutions that are used. Now, if you look at the kind of work that we do out there in the marketplace, we have a very strong relationship across a whole ecosystem where we work with OEMs, we work with engine manufacturers, we work with the fleet and end users, and then we work also with the refueling infrastructure companies, because very often, even though my product is supplied to an OEM and used by a fleet or an end user, it is extremely important that it integrates into an operational experience in the field where everybody feels comfortable and happy. And that is where the work with the refueling infrastructure and engines and all these people come in. So if you look at Hexagon in the hydrogen chain, we are what I would call as future ready. So we have right from 950 bar ground storage capabilities to 700, 500, 380 and 350 bar in the hydrogen space. Though we do have cylinders of 250 and 200 bar, they're normally not very much used for hydrogen applications. So it is 350 and above that really comes into play here. Now, if you look at the Indian renewable energy history, prior to the 90s, prior to the liberalization era, India was one of the largest and the biggest in the world in terms of utilization of renewable energy. And since then, while a number of other countries have grown, we have actually dipped to a large extent for various reasons. And today, when you look at the new clean energy story, you have options like CNG, which is licensed. Then you have LNG, which is open to all without any licensing, but only for automotive application. Hydrogen and electricity is again open to all, barring for statutory applications and requirements. So the challenge in the clean energy space in the country today, as we have seen, is that a market is slightly confused and investments as a consequence of that get delayed and fragmented between various options that are out there in the market, because almost all of them are being pursued with an equal vigor, if I may say so. And I think it's now time to reclaim the leadership globally by India in terms of renewable energy usage. So if I have to look at what we can offer for India and what we are suggesting and discussing, is one, let's say a car where you have multiple storage units up to 700 bar, but right now there are no such cars available in India. Trucks, as you can see, these are the products that we have actually been having in the marketplace currently. Trucks with multiple storage units up to 700 bar storage, but India is still at 350 bar and we have not yet graduated beyond that. Large bulk gas transportation solutions, which you can see on the right side, the last photograph, they could be at least 500 bar, but India is still at 250 bar in terms of what is used in the field and encouraged. Now, when you look at between trucks and buses, while both of them are options, the important factor here is why I have taken a truck is one long distance truck means even if you replace it with natural gas, I'm not even getting into hydrogen, means 20 cars are removed from the road in terms of emissions. That is the kind of emissions that a truck would emanate. So what a truck would need is range, and range means storage, and storage means obviously space on the truck. And that is where we come up with a lot of innovative solutions. Like if you see the one on the left, the storage solution is right at the back of the truck. Then I've shown you the figure of how this back of the cab storage looks like. And then this is a photograph of Hyundai, where again they have it at the back of the truck, but integrated in such a manner that it is completely hidden and not easily seen. Now, these kind of designs allow a truck to travel as much as 750 kilometers range. And that is what is crucial in the Indian context, because there is no point in trying to say that you're going to have something that is just a few hundred kilometers and then have a refueling infrastructure that is required. Whereas it has to be an alternative to diesel for a user experience to be interesting and attractive. Now, what happens in India is that we force fit the future into the existing for cost reasons, and that often becomes the stumbling block in progressing as fast as we can, actually speaking. Now, if you look at what is done globally, these are all solutions that we have provided. Whether you look at Mexico, Israel, Vietnam, Malaysia, Thailand, which are some of the countries being much smaller than us, they use very, very large units for transportation, whereas we still use very small units, as you can see in the picture at the bottom right. So the limit in India for transportation of gas is today about 9,900 liters water volume totally, whereas globally, they look at 40,000 liters plus. Now, the moment you move to something like 40,000 liters plus, your cost of transportation comes down drastically, and it makes a big impact economically for any user when transporting gas. Now, the factors that drive the design of a storage system for any customer is, of course, one is the weight, depending upon whether it is on road or whether it is on the land, the amount of storage that they would require. Then the application and usage, where are you going to be filling it into a truck? Are you going to be doing whatever it is with it? So that is another factor. And the entire flow chain from generation to application has to be mapped out. Now, the reason in the case of hydrogen that this is crucial is that if, let us say, you have a requirement of 350 bar on a truck and you are able to transport or store it at 500 bar, then the amount of compression or lack of compression requirements at the point of filling becomes very different when you have, let us say, storage at 250 bar and then you have to dispense it at 350 bar or maybe higher. So one needs to balance the costs between what it would cost for a compressor, what it would cost for a dispenser, and what it would cost for storage and transportation. which will then give you the best option of transportation in terms of either it is 350 or 500 or 700. And that is very crucial for any project to be successful economically. Now, the various factors that influence this decision is, of course, your capital cost, manufacturability, economies of scale, the return on investment, performance, the infrastructure available, and then, of course, the time to market, depending upon the demand that is there, all of that. Which leaves us with two things. One is you have available solutions, and then you have futuristic solutions, a lot of which the speakers before of me have spoken about and are going on. So what I'm talking about is the available solutions that are there in the market and being used since long. And that is the type 4 composite cylinders. Now, these are not only just available and proven, they are lightweight, 70% lighter than steel. There is zero corrosion or rusting, infinite fatigue life. So there is no question of metal embrittlement that could happen here. And in a fire, the behavior of a type 4 cylinder is very different from that of steel. And to that extent, offering a much higher level of safety. And as you can see, the strength of a composite cylinder is such that we have even run a battle tank over it without it, becoming pieces or whatever. That's the kind of strength it has. Now, one of the other aspects of what I would call as a fact of life coming from the industry is the users are not trying to save the planet, but the government would like to save the planet with a lot of policies and programs, while the investors who become the bridge between the users and the government, they need to meet the user demands and the shareholders' demands in terms of the return on investments and what they do. So all three different levels of interest need to converge. And what we feel from a convergence of interest would be a kind of a financial, where it could be maybe taxes, duties, subsidies. Second, which is more important to us, is the statutory aspects, wherein the new that is offered cannot be judged by the existing laws or systems, as a consequence of which, like I said, it becomes that much more harder to jump the hoops. And the third is allowing a policy direction and letting the market drive this going forward, depending upon wherever the money flows in, wherever the performance comes in. So this is a very, very quick and short presentation about what we are, and that's about it. Thank you.
Thank you, Dr. Ravindra. It's a wonderful presentation, and you exactly said the words like the market is a bit dilute, and then we are confused what to do. There are many options and we have to finalize that. That's really interesting. And one thing which I would like to ask is, you are concentrating more on the storage of hydrogen in the type 4 cylinders, but are you not looking at storing for ground purpose?
The same
Because
cylinders,
a lot of renewable energy is getting wasted, and the battery also cannot take that much of power. So the only way is to go for this hydrogen-based systems.
see, the composite cylinders can be used either for ground storage or for transportation or for onboard applications in an automobile. So you have all three options available with composite cylinders.
Yeah, but the thing is, it is very expensive. I can afford to use it for transportation application, but not for ground storage.
Well, I do understand, but the option that you have, which is today steel, is so heavy that sometimes even on a ground storage, it can have problems. Like, for example, I can tell you at a particular project we are now talking about, the size of the steel cylinders are limited, whereas we can have very, very large sized composite cylinders. Like I said, each of them about 8,500 liters water volume, which will then reduce the infrastructure required in whatever you're setting up. And then because of the lighter weight, There can even be innovative solutions like where it can go on the roof of a building. Whereas these kind of solutions are not being pursued right now because the focus is on steel, and then they say it is extremely heavy. And we have found in the marketplace that the return on investment on this, when you combine, especially for hydrogen, when you combine the lifetime cost, this ends up far cheaper than steel.
And you are also mentioned that we cannot go beyond 250 bar in India. Probably, I think you need to talk to government to increase the pressure range. Somebody has to build the cat.
That is exactly what the industry is doing.
I know about for about 4 or 5 years, everybody talks about that, saying that no, we can't go beyond. So somebody has to do that. So I think
we are already doing that. We are already doing that.
I know many people are doing that, but I think as a group, you have to go and get that. Okay, recently
I agree.
Yeah.
I agree with you.
So now the floor is open for any discussion. Anybody can ask some questions. You can raise their hand.
So let me ask one question. My question is to Ravindra. I mean, how do you foresee, let's say, next 10 years, the industry shaping up with this cylinder-based technologies? With the pressure coming up to meet the climate CO2 emission reduction cost, the green hydrogen coming up, and this ecosystem of the cost, with the additional cost of this compressed hydrogen, do you foresee that in 10 years, India as such, as a country, can adopt this or continue flourishing in this, or they have to come up with a new ways to solve this problem?
See, let me first give the example of what's happening in China, where they moved to a hydrogen economy in the recent times. And we are now in the process of setting up a plant there to manufacture more than 100,000 cylinders per year, which would probably be 3 or 4 times bigger than the biggest plant we have currently amongst all the manufacturing units globally. So that is the kind of focus that is there from China. Now in India, what, as I mentioned, is there is a lot of different options that are running, like CNG, hydrogen, LNG, electric. Now, even if I combine electric with fuel cell and hydrogen, it is still 3 different options. So what we felt, let me put it under the current circumstances, that in the next 10 years, probably hydrogen will grow, but CNG will probably have the predominant space, only because the infrastructure and everything required for that is in place.
Mm-hmm.
Now, for hydrogen to be successful, unless we move on to a regime of 700 bar kind of pressures on vehicles, it would be difficult for you to get a range. Because then the option would be that you got to have a massive infrastructure of refilling and distribution of hydrogen across the country. And it depends upon what option any investor takes, whether it is an Indian Oil or maybe anybody else who is working in this field. But the future is probably CNG and hydrogen.
Mm-hmm. So as a follow-up question, if you have to ask, or rather involve academicians, so those who are doing research in this and the different aspect of it, what would be the need of the industry to pose questions to them?
Okay, now that's a very difficult question to answer.
The reason why I ask, because you are in the industry, you may be looking at, let's say 10 years, 15 years, 20 years as the future scope and the growth of the business. And this, you may have phase 1, phase 2, and so forth. At some point, you may need some intervention wherein the academicians can play a role. Somebody who can do some kind of thing. So what would be those kind of things where you can have this collaboration going on?
See, today, I think when it comes to the manufacturing of cylinders, carbon fiber is the predominantly used material. To the best of my knowledge, I'm not aware of any other material that is being used. Though, of course, glass fiber is also used, but only for not more than 350 bar applications. But even then, the weight advantage you get there is very, very limited. Now, where academia could play a role would be two things. One, let's say, development of carbon fiber in India in such a way that we could have access to much, let's say, cheaper carbon fiber compared to what we have today elsewhere. Because one of the things is carbon fiber today is driven by the defense and aerospace industry. So consequently, when somebody gives me carbon fiber, he tells me this is what you have, take it or leave it. But then I may not need that kind of a grade, or I may not need that kind of a capability in the carbon fiber. So meeting the automotive or transportation requirements, can anything be done in this line? I think that could be one opportunity that could be there.
Thank you.
And then any other material that could come in? I don't know. I mean, that's a completely, big picture question for which I don't have an answer.
I think Dr. Akira has got a question. Please, sir.
Yes, sir.
You are muted, sir.
Okay, can I ask one?
Yeah.
And I want to ask to Professor Jayant Singh.
Yeah.
Yes, and as for the storage target, there are two main targets. One is to utilize the renewable, variable renewable energies as much as possible. The hydrogen is one good method. And another big target is international supply chain to make a long distance hydrogen supply. And as for the first renewable energy usage, what do you think the most preferable method for storage? That means, for example, higher pressure storage like that. How do you think about that?
Okay.
Yeah, quick answer will be appreciable, sir, because we have only 2 minutes left.
Right. This is a very difficult question because there's a lot of possibilities in that. But the point is, when you said renewable, you are saying that the input or whatever the methodology which you are going to impose has a green energy associated with it. And the material as such, if it is a porous material, so the hydrates are going to play a significant role in the future. And so this can have, of course, this pressure helps a lot, but pressure has energy associated with it. Ideally, it should have a low temperature. And if it is a temperature, if it is energy required to store it, then we do prefer to use renewable energy to use this kind of a temperature and pressure condition to store it. But what we foresee is that the metal hydrides can play a big role in that with a bit of higher pressure, but possibly less lower temperature.
Well, thank you very much.
Okay, with that, I really like to thank Professor Dr. Akira Ebe, Professor Jayant Singh, and Mr. Ravindra Vasisht for making this session so lively. And all of you are aware that the hydrogen storage is a very key enabling technology. As of now, none of the technologies meet our demand. So let's work together to meet the challenges and go forward. And I really thank the ICS Summit 2021 for giving us this opportunity to discuss about this particular really worth technology in front of all the people who are important. And I thank all the organizers for giving this opportunity. Once again, thank you all.
Thank you.
Thank you very much.
Thank you. Bye.
Bye-bye.
Bye.